Hello and welcome back. This is the second half of section 2.1. And we're still looking at frequency tables, but there are a couple more types of frequency that we can compute. So the first two types that we'll see are relative frequency and percentage frequency. So relative frequency is just the proportion of all data points that will belong to a particular class. Not counting totals, but looking more as a fraction of the whole. And percentage is the same way, where instead of looking at, say, more or less fractions, we're looking at just a percentage of the data points that belong to a particular class. So I think it's easiest to look at an example, so we'll look at the same example that we had before. So we had some test scores, and the number of students that got a particular test score ranged from lowest to highest test scores. So what we'll do is we'll look at, okay, so there were 2 test scores in the 50 to 59 range, 2 test scores in the 60s, 5 in the 70s, 8 in the 80s, and 7 in the 90s. Total, this gives 24 test scores. So for instance, the relative frequency of scores in the 50 to 59 range would be 2 out of 24. So this is just the proportion of students that had test scores in this range. You can see that it's just the frequency divided by how many, what's the total number of data points in the set. So this is fairly straightforward to calculate. So with 5 test scores in the 70s, that means that 5 out of 24 students were in this range. So this is the relative frequency. And likewise, once we have these proportions, we can turn these into percents. So 2 out of 24, this is about 8%. It's the same for 2 out of 24 again. 5 out of 24 is about 21%. 8 out of 24, that's 1/3, is 33%. And 7 out of 24 is about 29%. One thing that I'll point out is that if you were to add up the proportion of all of these relative frequencies, you should get exactly 1. Because then that would be the total divided by the total should be exactly 1. Likewise, if you add up all of these percentages, you should get 100. I believe here we end up getting 99. And you could ask, where did that last percent go? It's because we rounded these values, but we got close enough to 100 that we can assume for the most part that we have done this about correct. And then one last type of frequency is the cumulative frequency. The cumulative frequency is just a running total of all the frequencies for all the classes. So if we calculate the cumulative frequencies for our scores, we first start out with 2 because the first class in the 50s there were 2 students with that score. The next class for this 60 to 69 range, there is another 2. So cumulative, we have 4 test scores. Next, with 5, we'll have 9 test scores. So with 8, we will have 17. And then finally, the last 7 will join, and we get up to 24. A couple of things to notice. The last entry in a cumulative frequency distribution should be the same as the total, because it should just be the sum of all of the frequencies. Likewise, when we look at any particular number, for instance 9, this should be the sum of all the frequencies from that class and above. So this is exactly what cumulative frequency means. So we can so percentages maybe are a little bit easier to see than the frequencies themselves, and cumulative does give some nice information as well. Sometimes data will be distributed normally. And normally has a very, very specific meaning that we will address a lot this semester. And to briefly introduce it now, roughly what this means is that frequencies are going to be low on the extremes. So the further away you are from the middle, the fewer members in each class, but it will be higher in the middle. So maybe there will be somewhere between 1 and 2, or maybe 1, 2, or 3 very high number frequencies, in the very middle. And this should also be roughly symmetric. The highest frequency should be about equal to the lowest frequency, and so on and so forth into the middle. To give just a brief example of something that would be very normally distributed would be, say we're going to flip some coins. Here we'll flip a coin 14 times, and we record how many heads do we see. And we'll repeat this a bunch. So we'll repeat this experiment 50 times. So 30 of our 50 times, we flipped somewhere between 6 and 8 heads. 8 of those times, we flipped between 3 and 5 heads. So what you'll notice is that it's low to the outside, only 2 in each of the most extreme categories, but a lot right here in the middle. So what you'd expect, if you're going to flip a coin 14 times, you would expect about half of them will be heads, right in the middle. Also, this is pretty symmetric. The chances of flipping 0 heads is about the same as the chance of flipping all 14 heads. So the distribution, if we put it on a side, will look something like this. This is not a very good picture, but essentially the frequencies get highest in the middle, and then toward the outside they get pretty low, but also it's pretty symmetrical. So this is a normal distribution, and we will see this a lot this semester. And these last couple of comments, I'm just going to bring up the textbook to show you a few examples that will help sort of illustrate these sorts of facts, the sorts of information that frequency tables can reveal. So the first one is, if you look at the last digits of data entries, sometimes this can tell you a lot. For instance, if you have an instrument that only measures things to the nearest, say, 10, the last digit will always be 0. If your only measurements are things like 10, 20, 30, 40, all of the last digits of those are going to be 0. And I'll show you an example of this in a little bit. Gaps in frequencies can also reveal distinct groups. So for instance, if there's a huge gap in the data and we've got a lot of small numbers and a lot of big numbers, maybe those are coming from different sorts of things. And then lastly, you can actually put multiple frequencies on the same table to look at. So here is going to be a table that will look at where it's looking at the last digit of a device that's measuring pulse rate. And what you'll notice is that all of the even digits show up a lot, and it never shows up as an odd digit. So even though there's 455 times we got a reading with a 0 as the last digit, we never got one with a 1, a 3, a 5, a 7, or a 9. This would indicate that the instrument that we're using to measure with only does things to the nearest even number, and it will never give an output including a 1, where the last digit is a 1, 3, 5, 7, or 9. As far as gaps in data, so here we have a table giving the weight of randomly selected pennies, and what you'll notice is that between 2.4 and 2.59 there were 18 plus 19 pennies in that range, so nearly 40 pennies in this range, whereas down here we had what is this, 35 pennies between 2.9 and 3.2, but there's a huge gap in between. This might indicate that some pennies were made this small, a lot of pennies were made this small, and a lot of pennies were made this big, and maybe they came from different batches, for instance. So it might indicate that either something went wrong or they used a different mold, but for some reason some pennies are clustered around this weight and others are around this other weight. And then finally, putting two or more frequency tables on the same, putting two or more frequencies in the same table can help us look at differences between things. So here are service times at various fast food restaurants. So here we can see that McDonald's is clearly taking a lot longer as far as in terms of how many seconds it takes to get service as opposed to Dunkin' Donuts. So there is a lot of information that can be gleaned from this.